The purpose of this project was to send commands using a serial terminal to the microcontroller, as well as using Bluetooth to communicate between a microcontroller and smart device. UART is a universal asynchronous receiver, transmitter frequently used in communication between computers. We are to become familiar with the concept of the UART and ways to communicate through serial interface such as real-term, PuTTY, teraterm, and so on. In addition, we are expected to use IR communication. IR is an infrared signal that is invisible to the naked eye, yet is detectable by certain hardware components. In this project, the purpose was to expand on Project 3 by adding IR functionality as well as the LCD Nokia screen. IR will be used to facilitate communication between either of the two launchpads. The first launchpad MCU1 will act as the transmitter and the other launchpad MCU2 will act as the receiver, and will decode IR signals. MCU1 will serially communicate with a serial profile Bluetooth device to determine the commands to send out via modulating the IR LED. Character 07 will decide which command is ran. In addition, push button 1 will determine the device number on both microcontrollers. On reset, device 0 should be active by default. The following LED colors will indicate what is the current device mode on MCU1 and MCU2. Red LED, device 0. Green LED, device 1. Blue LED, device 2. White LED, device 3. Also, the IR signal must demonstrate the ability to transmit wireless data. Command 0 will display animation 0 on color LCD. Command 1 will display animation 1 on color LCD. Command 2 will display animation 2 on color LCD. Command 3 will display animation 3 on color LCD. Command 4 output a 262 Hz sine wave. Command 5 will output a 262 Hz square wave. Command 6 will output a 262 Hz triangle wave. Command 7 will output a 262 Hz sawtooth wave. First we will get into the first microcontroller's necessary components. The PLL.C file utilizes the onboard crystal to enable a clock and set the bus frequency. This module is required to use timers effectively in the grand scheme of the project. The bus frequency is set to 50 MHz. All timers and interrupts on this project will use this designated frequency. The UART.C file sets up and enables the UART connectivity on the TM4C. UART_INCHAR outputs the ASCII code from the UART receiver module. UART_OUTCHAR grabs an 8-bit ASCII parameter and sends the data to the UART transmitter module. UART_OUTSTRING uses UART_OUTCHAR iteratively in order to transmit an entire string. UART_NUDEC receives an ASCII character and converts it into a readable 32-bit unsigned number. UART_OUTUDEC grabs a 32-bit unsigned input number parameter and converts it into a readable digit 09. UART_INUX accepts an unsigned hexadecimal input and converts it to a 32-bit unsigned number. UART_OUTUX grabs a 32-bit unsigned input number parameter and converts it into an unsigned hexadecimal format. UART_INSTRING accepts ASCII characters from the serial port and adds them to a string until enter is typed or the maximum length of string is reached. The UART_C.C file sets the UART to interface the two microcontrollers. The port.C file initializes port F pins for output. It sets the PWM for the onboard blue LED. The UART_BT.C file sets up the communication line between MCU1 and the Bluetooth module. MCU uses pins PD6 and PD7 to communicate UART signals. Now we will get into microcontroller 2's files. The PLL.C file utilizes the onboard crystal to enable a clock and set the bus frequency. This module is required to use timers effectively in the grand scheme of the project. The bus frequency is set to 50 MHz. All timers and interrupts on this project will use this designated frequency. The port F file initializes port F pins for output. If a green LED is displayed, MCU2 is working. In this project, the blue, red, and green LED colors are utilized. The DAC.C file creates an 8-bit digital to analog converter. This is done with pins PB7. The reoccurring samples are taken using a CECS tick clock. The UART_test.c file troubleshoots on the PC serial terminal. This is done with a wired USB connection that communicates data from the MCU2 to the PC serial terminal. The SD7735 file contains all the methods and modules specific to the Nokia SD7735 screen. This is how values and shapes are able to be displayed on the Nokia screen. The artist_main.c file contains the main method. In this method, we call and configure all of the dependent modules. We also grab information from MCU1, and either stop or return sound through the speaker. Depending on the value grabbed from MCU1, that is how we decide what output to send. The main method reads the value from MCU1, and if 03 is chosen, that value is displayed on the Nokia screen. If 47 is chosen, a value is sent to the ADC which is then sent to the speaker. The way our output worked, if values 0 through 3 were sent to the terminal, that digit was displayed on the Nokia LCD. If values 4 through 7 were sent, a sound wave was sent to the speaker. Values 4 sent a sine wave. Value 5 sent a square wave. Value 6 sent a triangle wave. And value 7 sent a sawtooth wave.